For our next speaker, I have the huge pleasure of introducing Professor Darve from Stanford University. Professor Darve is an expert in mechanical engineering, and so we'll hear again about PDE constraint control. He received the Oshman Faculty Scholar Award and the Clark Faculty Scholar from Stanford University. He also received the Allen Award from NASA and the Leslie Fox Prize in Numerical Analysis from the IMA. Thank you so much for having agreed to speak at this conference.
All right, so yeah, thank you very much for the invitation. Yeah, it's great to be speaking at this workshop. So can you guys see my my screen? Is it working? Yeah, it's a little confusing to have the Zoom and the presentation at the same time. So if there I'm probably not going to look at the Q&A and the chat during the presentation. So if there are questions, maybe the organizers can interrupt, or you know, otherwise I'll ask.
You want me to stop you if there's a question in the Q&A?
Yeah,
or you prefer to deal with them at the end?
It's up to you, but I feel it can be
okay.
It can be more sort of interactive and lively if there are questions during the talk. But I mean, yeah, I'll let you.
I'll stop you. I'll stop you.
Okay. Just whatever works. Since it's a 45-minute talk, I figure there's a little bit more time. So okay, so I'm going to talk about so essentially control problems, PDE constraint control problems, but with a combinatorial control, and we're going to be using deep reinforcement learning algorithms. So the type of algorithm that, for example, were used for AlphaGo. So yeah, my name is Eric Darve. So I'm in mechanical engineering, but my training was actually in computational math at ENS Ulm and Pierre-Marie Curie in France. And this is joint work with Grady Wong, who is a PhD student at Stanford, and my colleague Adrian Liu in mechanical engineering. So here's the application. So there's going to be very little in this talk about you know, sort of modeling and you know, I'm going to look more at the sort of mathematical and numerical problem. But I wanted to kind of motivate a little bit the problem we're looking at. So the motivation comes from 3D printing, and in particular, so metal 3D printing. So it's additive manufacturing. So essentially, so there are different techniques that are sort of kind of illustrated in these movies here. But the basic idea is shown at the top right here. So you have a bed of metal powder. So there's this this thing that deposits a very thin layer, and then you have a laser that can move, you know, in the XY plane above the metal powder, and the laser is able to melt or sinter essentially the metal beads, and the laser can move sort of at more or less arbitrary locations in this 2D plane. So you can shine the laser at any location you want, and melt the metal. And so you do this layer by layer, and with this process, you can essentially build pretty much any 3D shape that you want. Okay, so this is a very powerful technique. So there's a lot of companies now that you know, can do metal 3D printing, but there are many challenges. So in particular, it's relatively difficult to ensure high quality part compared to, for example, using a mold or more traditional sort of techniques from in metallurgy. So for example, the parts often have low strength, and there is this problem of residual stress. So this comes from, you know, the rapid heating and cooling of the metal during the printing, and so there's a lot of residual stresses in the parts. So for example, this can you can get distortion, like this is shown here on the bottom right. So the part is supposed to be flat, but because there is this stress inside the printing component, then there's a slight bend. And you get all the problems with microstructure, distortions, cracks, and so on. And so what we're interested in here is there a way that we can optimize the path of the laser in order to improve the quality of these parts. So again, there's not going to be a whole lot on the details of the modeling. Instead, we're going to sort of look at a simplified mathematical problem, but we're going to see that numerically this is still very challenging to solve. And then, of course, you can expand on this work by looking at more accurate physical models and so on. So, so this is going to be a PDE model for the temperature. So phi is the temperature of the metal. So it's a, a heat diffusion reaction equation. So hopefully you guys can see my my mouse. Maybe it's small, but okay. So it's 2D heat diffusion. So you have d phi dt, so temperature over time, Laplacian of phi, and the h phi term is basically the heat conduction with the layers below the one where you're currently printing, and then you have this term. So x bar y bar is basically the location of the center of the laser at time t, and then the laser has a certain shape, so circular shape, or it could be sort of a Gaussian shape, which is given by this this function u here. And so as you move the laser, so essentially as you move x bar y bar, you're going to raise the temperature of the metal, and hopefully above the melting point, and then you can start printing your 3D shape. Okay, so here is the objective function that we picked. So again, it's a sort of a simplified mathematical model, but then we're going to be more concerned about the numerical solution to this problem. So here the idea is that in order to sort of avoid this residual stress, and there are different objective functions that could be used in this modeling, but we picked this one here. So the idea is we want to keep the metal above a certain temperature, this phi threshold, as long as possible, in order for essentially the residual stress to relax. So our objective function is it's integral over time. So we want this to happen for as long as possible. So we have this indicator function phi minus phi threshold, and then we integrate over the 2D plane of the sheet we're currently printing. And so we want phi to be above phi threshold for as long as possible. And the right, and so the difficulty is that the laser can move in pretty much arbitrary ways. So this is, for example, on the right here, sort of showing a little square that we're printing. And so the way we're modeling this is we're assuming that so again, this is a simplification. We're discretizing the piece. So this is in the 2D plane, the current layer we're printing. We're discretizing into discrete tiles, and we're assuming that the laser is being shined on each tile with this u function. So the laser is being shined on each tile and then moves to a different tile. So for example, it starts at A0, jumps to A1, A2, and then A3, 4, 5, 6, 7, 8, 9, and so on. So it keeps moving around with the goal of maximizing the objective function. Right. So the goal is to visit all tiles once, and then we want to optimize the sequence in order to maximize the objective function. So just for sort of illustration, this is just a simple kind of example to sort of see what's going on with this. So this is showing so you have x, y spatial coordinates. The z is the temperature, and so we're moving the laser in this. So here, very simple order. So lexicographic ordering. So we're moving, well, actually along y first, and then along x. And so as we're moving the laser, you can see the temperature rising, and then you can adjust the power of the laser to essentially, achieve whatever temperature you want. And so you can see that if you modify the path of the laser, then you're going to get different temperature distribution. and you're looking for essentially the temperature distribution that stays above this threshold temperature for as long as possible. Okay, so, all right. Sorry, I'm moving a little bit my windows around to make some space. And so this is, so here I'm going to focus on this heat diffusion problem, but we're hoping that the methods we've developed apply to a broader class of problem. So generally speaking, this is a problem of optimal control with PDEs. So we want to maximize, an objective function using this control. But what's special is that the control is combinatorial. So mathematically, we can think of it as finding a permutation. So here, n would be the total number of tiles that we're trying to print. So we want to find a permutation that maximizes our objective function. So it's the combinatorial PDE problem. So before moving on and sort of explaining how we approach this problem, I want to sort of mention a little bit the current state of the art, so to sort of set the stage a little bit. So in terms of combinatorial optimization, so this is the problem we're looking at, the sort of classic technique for combinatorial optimization is a sort of traveling salesperson problem. So where you have a list of cities, distance between cities, and you want to visit each city exactly once, and you want to find the shortest possible route. And so there are many, so this is an NP-hard problem, but there are many heuristics that are extremely fast and effective for this class of problem. So I want to immediately mention, because this is a question we often get, that this is different from our problem because essentially in the traveling salesperson problem, the objective function, so the cost of taking a route is sort of fixed. Whereas here, in our case, the cost function is essentially history dependent. So it's a type of a TSP problem where the cost of each route sort of changes as a function of the cities you've visited so far. So it's a different. So we're solving a different problem, but it has some connection to this TSP. So I'm going to compare in terms of reference benchmark techniques. I'm going to compare against MPC, which is the so-called model predictive control method. And in this algorithm, there's essentially a finite horizon. So we just look at the next few moves. And then for just these next few moves, we're going to essentially brute force it. So we enumerate all solutions, estimate the cost function that we have for these sort of partial solutions. And then we take the best one, and this only determines the next best action. So essentially the next tile that the laser is going to shine on. And then we so this might be, say, the first action, and then we go back to step one for the second action, and we just keep repeating that. So the idea is by looking at the finite horizon, we can keep the computational cost small, but of course it's an approximation because we sort of never really see the entire path until pretty much towards the end. But it's exhaustive, so at least the finite horizon optimization is sort of exact at every step. Then another popular technique, so very simple, is k-opt. And so in this technique, we essentially do sort of local perturbations of our current solution. So we start from some given guess. So it might be this lexicographic order. You first move along X and then move along Y. So given this current guess, then you pick K elements. So K is small, might be, for example, 3, 4, 5. And then you apply a random permutation to these K elements. And then if you get a better, if the objective function has increased, then you keep this new permutation. Otherwise, you just keep the one you have, and you just sort of keep repeating this approach. So it's very simple. Of course, the downside is it's somewhat mindless in the sense that there is no guidance whatsoever as to which permutation you should look at. You just sort of randomly trying out. But on some problems, it can work quite well. So here is just sort of an outline of just the end of the presentation, showing the improvement that we got with our method. So R2 is a variant of AlphaGo. You have this MPC, which is this model predictive control, and then this KOpt with K equal 3, and then our method in blue here. And the statistics essentially measures the deviation from the mean in terms of standard deviation. So here you can see that on this problem, we were able to find solutions that are 15 away from the mean in terms of the objective function. So huge improvement using our technique. So let's see a little bit how this was done. And so we use this technique of reinforcement learning along with a deep neural network. So this is similar to what was done for AlphaGo, and AlphaGo has clearly some similarities. So we're not doing metal 3D printing. We're playing a game of Go. But it's a sort of a similar problem. There's a board that's 19 by 19. And you want to figure out, so here the way to play Go is sort of, where to place your stone, which can be interpreted as, which tile your laser should shine on, and and in the right order. So I'm going to give you more details on this method, but it's based on using the Monte Carlo tree search. So you build a tree of all possible moves. And then there's a smart strategy to sort of visit only the subtrees or path that are the most promising. So this is so it uses this technique of reinforcement learning. So it's a very powerful technique because it's sort of very general, really makes very few assumptions. So it's applicable to really a broad class of problems. So first, we use a deep neural network, or a series of deep neural network that are used to rank the possible next moves. So more specifically, for example, if we look at this this board right here, so you can place a stone at every intersection here, and so what the DNN is going to output is a probability. So numbers between 0 and 1, and if the probability is close to 1, it means that there is a high chance that this location is the best, the one that has the highest chance of winning, essentially, whereas a low probability means that it's likely to be sort of a bad move. So the DNN is trying to predict this. So this is sort of predicting the so-called policy. And there's another component of the DNN that predicts the value. And the value is basically the strength of a current position, right? So essentially, again, it's a probability of sort of winning, but just based by analyzing the current position. And so the way AlphaGo was essentially implemented is that there is a self-play strategy. So the computer plays against itself, generates new moves, and then is able to improve its learning, to improve its deep neural network using these new moves, and then just keep sort of repeating this process and progressively making improvements. So really, what you need to do to make this work is you need to be able to play the game many times. So the sort of forward simulation should be reasonably computationally cheap, right? Should not be too expensive. And then simply you need, at the end of each game, to be able to measure the score. So here are the sort of more details on what AlphaGo is doing. So I'm not giving you all the technical details because there's a lot of technical details and it would take a little bit too much time. So this is sort of just a high level view of things. But so AlphaGo starts by playing a large number of games against itself, and this generates a large training set of games. So some of the games are won, some of the games are lost. And then based on this, the deep neural network is improved. So essentially, the deep neural network, looks at which games were won and which games were lost, and then based on that, compare against its own prediction, and then using the usual gradient methods, makes some improvement to its own predictions. And then once you have this improved deep neural network, so you have essentially, you've created a better player, then you go back to step one, you play another round of games and so on, generate a new training set, and just sort of keep repeating this strategy here. So this worked well for Google. This was a good fit, I guess, for Go and chess and many other sort of board games that they tested their method on. But they had access to massive computational infrastructure, and actually a lot of the software development really went into parallelizing the code and being able to leverage several TPUs and so on. So in any case, this type of resources is is not accessible for university or for most research groups. And so we looked into, we tried this strategy, but the convergence was not, was really not good enough. And so what we did is propose a new strategy that combines this idea of Monte Carlo tree search and DNN and deep neural network with the K-opt strategy I talked about. And this gave us a very significant improvement in computational efficiency, and so we're able to solve very large problems with our new technique. So this is sort of an outline again of how the algorithm works, and then I'm going to discuss in more details our strategies with the Monte Carlo tree search and the K-opt algorithm. So the first thing is, but this is sort of almost a minor comment, is that when you play Go or chess and so on, these are two-player games. But here, when you do the laser path planning, you can still view this as a sort of a game that you're playing against the laws of physics as implemented using the your PDE model. And so similar to AlphaGo, we're going to have a deep neural network and a Monte Carlo tree search strategy that's going to be used to explore different permutations, different laser path, and make recommendations for the next tile to be printed. But contrary to AlphaGo, we only use the deep neural network and the Monte Carlo tree search to only produce or construct the current best guess, or current best guess for the laser path. And because this is already quite expensive, and it's really not possible to generate an entire training set with this strategy. And so instead we use the K-opt algorithm to start from this current guess and then generate a new set of laser path or laser trajectories, so a new set of permutations based on this current guess. And then we extract from this set some of the top permutations, and then we retrain our deep neural networks using this new set. So after that, we now have a deep neural network that is capable of making better predictions, of producing better laser path. And so now we can go back to step one and regenerate a new current guess and apply K-opt again to generate the training set, and just sort of keep repeating this process. So I'm going to explain the different components of the algorithm. So the first one is the Monte Carlo tree search. This is the algorithm we use to generate our sort of current best guess, and so this depends on the deep neural network that we've trained up to now. So here we follow the strategy that was in AlphaGo and AlphaZero. So it's a variant of the so-called PUCT algorithm. So the predictor part of PUCT is basically the deep neural network. And then the upper confidence trees algorithm is an algorithm that reduces the so-called regret. And so So I'm going to explain this in a second. So again, the deep neural network is used to propose the next move. Okay, so this I explain. And then the way that we explore these different action sequences is using a combination of exploration and exploitation. So so essentially the high level idea is you have this tree shown on the right here of all possible games, and you cannot possibly explore the entire tree. The tree is just too large. And so what you want to do is you want to focus on the path in the tree that seem to be the most promising. So this is the exploitation part. And you want to couple that with some random perturbations. So essentially every now and then you want to explore a path that you're predicting are to be suboptimal, but since your model is your DNN is inaccurate, you need to do this exploration to check if by chance you may have missed actually the correct answer. So for example, your DNN may predict go to the right, but actually the correct answer is go to the left. So you need to include some random component to your algorithm so that you explore what seems to be suboptimal paths to sort of check that indeed they're not as good, or maybe just discover that there was a better path down this road. Okay, and I have another slide. I will go into some more details. But once you reach the bottom of the tree and you have a complete path, then you can evaluate the objective function. So this is sort of more of the details of how the algorithm looks like. So again, you start at the top. So your deep neural network is making some recommendations. For example, here it's saying you should go to the right here. So place your Blackstone at this location here, and then it's recommending going to the left. And so, for example, when you reach the left here, this is a new node that you have not explored yet. So you just sort of initialize this node, okay, so I'll explain this in a second, but before moving on, so I want to again explain this exploitation and exploration idea. So this is implemented in this PUCT algorithm. So exploitation means that if, for example, the DNN is telling you to go first take the right step and then take the left branch here, then hopefully this prediction is correct. So these first two moves are correct. So you want to keep exploring subtrees that are below. So this is the idea of exploitation, right? You're assuming that your current guesses are quite good, and then you want to keep exploring the subtrees to find whether the optimum is down in that subtree or not, or where is it. And exploration is a different concept where, well, perhaps the choice of going right was not optimal. Actually, you should have gone left. So you want to introduce some randomness in the algorithm such that what looks like suboptimal options are explored as well. So this is the exploration path. Okay, so this is the sort of select, expand, and evaluate steps. And then the backup. So this is so you have this. The neural network outputs two things. It outputs the policy, which is recommending a move, and it outputs a value, which is basically how strong your current position is. Basically, the probability of winning from the current position, regardless of assuming that you're going to play sort of perfectly or very well after that. So this is so you have this value v, which is assigned to every node, and then the neural network is used to predict this. And so when you explore the tree, you don't want to, or you cannot. This is go all the way down to a terminal leaf node. Initially, you just explore you start exploring from the top. You discover a new node, and so what happens is, so this is a new leaf node, and you want to immediately backpropagate. So what you do is you use your neural network to actually predict what is the value of this new node you've discovered. So this leaf node that you've discovered, and then what backpropagating means is that every node stores Q, where Q is essentially the average score for the corresponding subtree. right? So it's basically an average of all the objective function evaluations that you have in that particular subtree. So if you discover a new leaf node here, V, then all the Qs are averages. So essentially, you're going to use this value V to update all the averages that, starting from V and going up the tree till you meet the root. So this is what happens initially in the game. But as you keep exploring, you're going to keep expanding your tree and so on. At some point, you're going to reach a terminal leaf node. And at that point, you can actually evaluate your true objective function and sort of backpropagate now the accurate, the exact score or value for the objective function that you have for your complete path. And so now you're simultaneously training the deep neural network to learn this V or Q value, and also you have a deep neural network to predict the policy again, which is the best next move. All right. Okay, and so you keep sort of exploring the tree. So you have another parameter, which is total number of rollouts. So basically, how many times you're going to repeat this sort of ABC steps. So this is repeated a fixed number of time, and then once you're done, then you just simply look at the node that was the most visited. So maybe this is the black stone at this location here, and then you decide that this is going to be your next move. Okay, and now this becomes the new root of the tree, and you just repeat the same process. You do another set of M rollouts starting from this new location to determine the next move, and just keep going like this until you reach a terminal leaf node, and then this is your current best guess. So this is what the so some more sort of technical details what the deep neural network looks like. So it's a 3D tensor.
So we have a question in the chat.
Yeah.
So for the previous slide, the question is, what is the terminal cost function used in the example?
So the cost function is the one I had at the beginning. That's basically the objective function that you have for your optimal control problem. You're checking for this temperature being above the threshold temperature. Yeah, I can bring up the slide again. So this is basically, sorry, let me just jump up. That's the objective function. So once you reach a terminal leaf node, you basically have an entire trajectory. So you have this 36 tiles all visited now, and so you can evaluate the integral from 0 to TF is now sort of complete. So you can evaluate your objective function exactly. So you have two steps. One where you use the deep neural network. So let me jump ahead. When if you don't have a terminal leaf node, then use a deep neural network to predict the objective function. And when you reach terminal leaf node, then you can compute exactly what the objective function is, and then backpropagate the correct value.
Eric, we have another question as well. Sorry.
Yeah, sure.
Can the final possible action be based on Q function instead of a frequency? What is the difference?
Pretty much the same thing. Yeah, that's a technical question. I mean, basically, the formula for the action is shown here on the top right. So the action we're picking is the argmax of Q, which is basically the more or less the average of the objective function for that subtree, plus P, where P is this probability as generated by the deep neural network. So now you have this term with the square root, which is the sort of exploitation term in PUCT. So the node you've most visited, I would say, should match the largest value of Q. But okay, depending on how things done, if some Q values are very close, then it might be slightly different, but it's quite close. So I'm not sure exactly, the technical difference. You can try to pick the maximum of the argmax of the Q value. But in the original AlphaZero, and this is the strategy we picked, you use the action that was visited the most, but they're closely related. Any other
Thanks.
question?
No, I think we're good so far. Thank you.
Okay. All right. So and basically almost done with the algorithm. Going through some benchmarks. So it's the structure of the deep neural network. So this is kind of again, these are sort of practical details. You know, not necessarily a lot of theory behind this, but this is, you know, some of the detail that sort of make the method work. So the first thing is, so n square is basically the board is n by n. And what we do, so we have a stack of 2D tensors. So each sort of image here is an n by n tile, and then we, you know, sort of stack it up in a third dimension. And so we have 10 essentially 2D boards that are stacked up. So the first five n square, this is the field history. So it's basically the history of the temperature field during the last time steps. Okay, so current temperature, T-1, T-2, T-, so on, T-5. So this is the field history. And then we have another set of 5 boards, which essentially contains information about the tiles that have been visited. So there's sort of a numbering scheme, which, you know, in each tile that shows you, you know, the tiles that have been visited during the last 5 time steps. And then after that, you know, we sort of adapted our neural network based again on this AlphaZero. So initially there is a convolution network, convolution layers, and then after that there is a number, so a large number, so n. So for example, n, if you have a 6 by 6 board, we decided to pick 6. So these are residual layers. So from the ResNet, so convolution residual layers, and then the output, as I mentioned, you have actually two heads or 2 outputs. One is the policy, so the recommended move, and one is the value prediction. So what is the essentially you know, probability of winning. Okay. Okay. So again, you know, as I mentioned, MCTS, this Monte Carlo tree search, is used only to generate the current best guess, and in AlphaGo, you know, the Monte Carlo tree search is essentially used to generate the entire training set for the deep neural network by using self-play. So instead here we use kopt to generate our training set and improve our deep neural network. So this is the kopt strategy, but so it's essentially we use kopt the way I described. So you start from the current best guess. So this is generated using the Monte Carlo tree search and the deep neural network. Then you pick k entries in the permutation. You randomly permute these entries, right? So you keep doing this a large number of times. And so this generates now a very large set of permutations. You select some of the top permutations, and this is going to form your training set to improve the predictions of the deep neural network. So one of the reasons why this algorithm actually works very well.
Yeah. Sorry to bother you. We have 2 other questions.
Sure.
If you, yeah, thank you. The first one is 2D tensors, I believe, are matrices. How do you stack a 2D tensor into a 3D tensor? Does the ordering matter?
Well, so I don't know, this is sort of a maybe terminology. So basically what I mean here is it's a stack of 2D of matrices, right? So basically you have the IJK indexing, right? So maybe IJ would be the XY you know, space indexing, and then the K would be, for example, 0 through 4 might be the field history, and then 5 through 9 might be, you know, the tasks that have been visited. So the ordering doesn't matter, right? This is the usual. I mean, in deep neural networks, convolutions, you know, the ordering, the way you stack things, don't matter. However, of course, the features you pick, you know, picking the temperature history for the 5 last time steps and the tiles that have been visited during the 5 last time steps, that choice matters. But the way you stack up the boards, essentially, that has no impact on the performance of the algorithm.
Thank you. And another question, do you include the history of your solution to become non-Markovian in some sense, or simply to tell which squares were already visited?
No, so the Yes, basically the history is because you know the neural network doesn't see the PDE, right? So it doesn't. So since it doesn't see the PDE, if you just show one temperature field, it's very difficult to learn how the temperature is evolving in time. So essentially, the temperature history is sort of a way to help the deep neural network learn the PD that governs the evolution of the temperature. And then the second set of tiles basically has to do with providing information about the control. So essentially, what control was used, you know, which is basically this laser motion during the last 5 time steps. So this is yeah, this is similar to the game of Go actually, where, for example, you know, you have this problem of how do you encode the order in which the stones, like for example, the last 5 stones were placed. And the way to do that is actually to feed the neural network a number of boards where you know you have the state of the board at different time steps, and so that tells you, that allows the neural network to kind of figure out what were the tiles that were last you know visited and in what order, and then make a prediction based on that. Of course, this is, you know, obviously heuristic. I mean, it's not that there is necessarily a strong theoretical justification for this, but this is what empirically, you know, works best for this class of problems.
Thank you.
Right. So I'm not sure where I just stopped here. So I was talking about the yeah, right. So yeah, so that's right. So one of the reasons why KOpt is working very well is that, well, first of all, it's very, very fast. It's much faster than running the Monte Carlo tree search, but also for this particular problem, and that's, I'm going to conjecture that this is true for many sort of optimal PDE control. The new permutations that are generated using KOpt actually are meaningful, in the sense that many of them actually do provide an improvement over the current guess, right? Like a bad strategy would be one where, you know, most of the new permutations are worse than the one you started with, and that would be a very inefficient method. But here, essentially, the rate of success is actually quite good. You actually, many permutations are actually an improvement over your current guess. So it's a very efficient strategy. And then it generates, you know, diverse and high quality data that's, you know, works very well with the you know, the training of the deep neural network. Okay, so so I guess, you know, I was a little bit slowed by the questions, but, you know, I'm going to show the benchmarks. So this is just sort of a summary of the algorithm. So again, you use a deep neural network with this Monte Carlo tree search to generate a new estimate for the optimal solution. Then the KOpt strategy is used to generate a new set of permutations in this local neighborhood. So you only permute K entries in your best guess. And then, so you have this very large set. You're going to extract, you know, a subset of the best permutations. Then you're going to retrain your deep neural network based on this set. So essentially, you know, I guess at the previous iteration, the deep neural network was not able to predict some of these better permutations. So you have to retrain the deep neural network to, you know, correct itself. And then once you have this improved neural network, you can generate a new best estimate and sort of keep going in this loop until, you know, you've reached something that you're happy with. Somehow the objective function is no longer increasing, or maybe, you know, you've exhausted your computational resources. So let's
Eric, sorry,
yeah.
I'm interrupting again.
No problem.
Yet another question. Why not keep the area hot with another heat source? I guess this is a very
another heat source.
Yes, this is, I guess, a general question from the.
Okay, so that's a good question. I mean, this is more in the area of 3D printing.
Yeah.
Well, yeah, honestly, I don't know the exact answer. There obviously, you know, for example, the sort of room or environment in which the printing is happening is already, you know, at a fairly high temperature. So they're trying to do that. But essentially, it's you know, it's a fairly high temperature, so it's very hard. It's very difficult to, you know, to maintain a temperature, you know, to maintain that kind of temperature during the printing. But you know, it is when the printing is done, there's often, you know, various type of thermal treatment that will, you know, improve the quality of the printing. So certainly there are many methods that are used to improve the quality. But here, you know, we're looking at, you know, just in terms of the laser, can we, you know, just by changing the laser path, make some improvement? But of course, this can be coupled with other techniques, and people use that obviously to improve the mechanical properties of the part. Another option, of course, is to print the same part multiple times and keep the best one, which is, you know, often what actually people do.
Thank you. If you're okay with that, I propose that I ignore the next questions because we're very close to the end. So
Okay,
you can,
okay.
you know, actually finish the talk, right? And and then
I'm getting there. Yeah.
Yep. All right.
Yeah, we can take some more questions. Yeah.
Yep.
Okay,
Yep.
so just
Thank
showing
you.
you the benchmarks now. So so the reference, you know, comparison algorithm. So there's R2, which is basically sort of a variant of you know, AlphaGo. So it's AlphaGo style algorithm. But AlphaGo, you know, it's something I didn't mention here, but you know, when you play Go, you have a +1 if you win, -1 if you lose, and maybe 0 if you have a tie. Whereas here, you know, we have our objective function is real valued. And so it is actually, turns out it's very important to convert this real valued objective function to +1 -1 score. And this is what essentially this R2 algorithm is doing. And we also, you know, used similar ideas to convert our real valued objective function to this +1 -1 score. So we're going to compare against R2. So this one, R2, is basically missing this k-opt, this k-opt step that we were using to generate the training set. Then you have the pure, you know, 3-opt. So k-opt was k = 3, where again you apply random permutations, and if you find something that's better, you switch. Otherwise, you keep the current, and then you just keep repeating this process. And finally, I mentioned the model predictive control, where you optimize over a finite or short horizon. So first, I want to show you 3x3 tiles. So 3x3. So this is a 9 factorial path. So a big number, but you can enumerate that. So so this is actually, on the left, you have the exact distribution for 2 different, essentially, PD models that, you know, are close to steel and titanium. Try to model steel and titanium. So this is exact distribution of scores, right, on with this semi-log y scale. And then here on the plot at the top here, you have the true maximum, which is achieved by 3-opt actually very quickly here, because this is a relatively small small board. So actually the brute force 3-opt is actually able to get that pretty fast. And the blue, our method, is so a little slower here, but is eventually able to find you know, the maximum as well. Of course, here the running times are quite small because it's very quick. So the point is, our proposed method at least is able to find the exact optimum on this problem. So now we extend to 4x4, 5x5, and 6x6. So the computational cost of brute force increases very rapidly. For example, 6x6, that's 36. So the enumeration is actually 36 factorial, and that's, you know, 10 to the 41 permutations. So here, you know, you cannot enumerate all possible paths, so we don't know what the exact solution is. And these distributions here on the left are sort of approximate. Just, you know, we just did a random sampling to get these distributions, but it's obviously incomplete. So we don't know what the exact maximum is, but you can see that our method in blue is significantly outperforming all other techniques. So MPC in red is actually doing pretty well in this example. 3-opt is also, sort of close behind. And then the R2 method, which is sort of the pure AlphaGo technique, is sort of very slow. So this is what I mentioned, that essentially this R2, which is sort of the AlphaGo, AlphaZero technique, well, if you have sufficient computational resources, probably would get to the blue. But you can see that it's because it's computationally very expensive, in terms of if the x-axis being the time, it goes up sort of very, very slowly. And the t-statistic here is basically, so t-statistics is the score, the value of the objective function, but it's you subtract the mean and you divide by the standard deviation. Essentially, this measures how many standard deviations away from the mean you are, and you can see that we can go as high as 15 standard deviation away from the mean with our method. So in all these cases, we definitely outperform the reference benchmarks by quite a bit. So these are examples of solutions. So maybe I'll kind of skip that, but this is showing, for 2 different types of solutions. So there are some interesting features where, for example, 0, 1, 2, 3, 4. So you combine sort of staying local, but sort of jumping around. Note that both solutions, we don't know whether they're optimal or not, but we certainly tested all sort of local permutations, and they're certainly optimal with respect to all these local permutations. So for example, the 3 here is kind of interesting. 0, 1, 2, and then you jump 3 here, and then you come back 4, 5, 6, and then you sort of do this space filling curve. The 3 kind of seems odd. For example, why not flip 3 and 16? That seems more local and make more sense. But actually, if you do flip 3 and 16, the objective function goes down. So there's something real about having this 3 somehow sitting here in this corner. So you get some non-trivial solutions. We did another PDE model. So this one is because we wanted to try a different PDE. So we tried the damped wave equation. So second derivative in time for phi. So plus of phi, and then damped with the kd phi dt. And again, we have a source term with x bar, y bar. So this is the location of the laser, and a slightly different objective function. So we want to essentially minimize phi this time. And again, we get very good results, where we're outperforming other techniques on this different PDE. The t-statistics are a little bit lower here, around 6, a little bit above 6. Okay, and so just wrapping things up. So this is showing as we increase the size of the domain, the cost of the different parts. So there's the Monte Carlo tree search, which I mentioned is very, very expensive. For example, the k-opt is extremely cheap. We can explore, a huge number of permutations. So that's why we had to switch to k-opt, because if you just use MCTS, then the cost is absolutely overwhelming. But one interesting thing is you can see that as we increase the size of the board, the fraction of cost remains roughly constant. So essentially, it's the different parts of the algorithm are sort of well balanced. So this is just future work, because we went all the way up to 6 by 6. Maybe with more computer powers, we could go to larger boards, but clearly there's a limit. So the idea is to apply this strategy in a sort of recursive manner or multi-scale. So essentially, you first figure out the best 6 by 6 board, and then, for example, you build another 6 by 6 board made of B1 tiles. So essentially, it's a 36 by 36 board, and you can keep repeating that. So it's a recursive sort of process. And then you can definitely build much larger boards with this strategy. So hopefully there's a path to building something that has a kind of a large, more realistic size. So just my concluding comments. So showed you some techniques based on, so for combinatorial optimal control of PDEs, it's based on reinforcement learning, and we combined the Monte Carlo tree search with deep learning. So this is sort of AlphaGo, AlphaZero style algorithm, and it's improved using the k-opt search, which allowed us to really reduce the computational cost tremendously, so that the problem was tractable with our resources. And so we had some very good success against the state of the art, and we're able to identify solutions that are, for example, 15 standard deviation away from from the mean. All right, so this concludes my presentation. So yeah, I'm happy to take further questions. I don't know if Grady is in the audience and can help with answers as well. Yeah.
Thank you. Anyway, first.
Yeah. All right, yeah, thank you, yeah. It's hard to be interactive with these Zoom sessions, but yeah.
All right, we do have the time for if there's a quick questions. I mean, you had many during the talk, so.
Yeah.
So I have one question for the.
Yeah, go ahead.
I have one question for the k-opt search. So, for the value of k. So in the talk, I didn't see you mention what value of k you used and what's the effect of different values k. For example, I assume if k is too large or too small, the result should be not small. We should choose some.
Right. Yeah. So good question. So I didn't show that bit, but yeah, it's a very good question. Well, if you want, I can share the results from the paper. But we did investigate different. So we optimized, various hyperparameters. So mostly, this k value, and also when we generate permutations using the k-opt algorithm, there is the question of what's the fraction of permutations that you keep to create your training set. And so, for example, for k-opt, so your analysis is correct. Essentially, if you use a k that's too small, then you're making very, very small moves. So you're very, very limited, and the odds of finding a better trajectory are small. And also, your improvement in the objective function may be very small, so you're learning very slowly. But if you increase k-opt too much, if you increase k too much, then it becomes very costly to generate all these permutations and do the down selection for the training set. So we explored values of k from 1 to 5. Essentially found that k equal 4 was seemed to be optimal. K equal 5, of course, as you increase k, your in terms of number of iterations, you're converging faster, but each iteration takes a lot more time. So overall, it's not as efficient.
Okay, thank you.
Yeah. Thank you. Is there any other super quick question? If not, let us thank our speaker again.
All right, yeah, thank you. Thank you, everybody, for following.
Thank you.
So
thank you so much.
Yeah, if you have further questions, you can send me an email, darve@stanford.edu, and then we'll be happy to answer your questions, share your code, or.
Sorry, that was.
So we have one extra question in the chat, maybe.
I don't. Oh, yeah, just got it. Sorry. Have you considered?
So somehow I'm not seeing any questions in the Q&A. I think only.
No, it just got one in the chat while I was saying there was no question anymore.
Okay.
Have you considered using GNNs for the combinatorial optimization problem?
So the graph neural networks?
I think so.
So I have to admit, I don't understand the question. I mean, there is no graph per se. I mean, there's a graph in the traveling salesman problem, but as I explained, this is problem is fundamentally different. Can't really write it as a graph.
I don't see a follow-up. Anyway, I'd suggest that they write to you if needed.
Yeah. So again, you can. I should have added my email here, but yeah, you can write me at darve@stanford.edu, and I'll be happy to answer your questions, or share the code, or discuss this further. Yeah. Thank you.
Thank you.
All right.
All right, let's move to